Hi everyone! In this video, we're gonna calculate the work done from pulling a spring using Hooke's law. So let's take a look at this problem. A force of 10 pounds is required to hold a spring stretched 4 inches beyond its natural length. How much work is done in stretching the spring from its natural length to 6 inches beyond its natural length? So these types of problems, they sound hard, but they're really not, because there are 4 steps that you need to know. The first step is to draw the diagrams, and I'm going to show you how to do that in a second. The second step is to convert the units on the x-axis. So if we get force is in newtons, the distance in meters, then the work will be in joules. Now, if the force is in pounds, the distance is in feet, then the work will be in feet-pound. So this is the convention that most textbooks use. The third step is to find k if it's not given. And k is in this formula, which is work is equal to the integral from a to b of force times dx, where force is equal to k times x. So k will just be a number, it's a constant, and x is the distance that you are stretching the spring. And this is also known as Hooke's law. So go ahead and pause this video and write this down, and we will solve it together. Let's start with the diagrams. So we have a spring like this. It is at rest, so you're not pushing it, you're not pulling it, you're just letting it be. So it is at rest, and we also have an x-axis looking like this. And the point at rest, this point, will be considered 0. The problem says that a force of 10 pounds, so a force of 10 pounds, is required to hold a spring stretched 4 inches beyond its natural length. So naturally, it's resting at 0, but we're pulling it 4 inches. And we know that the force is 10 pounds. Lastly, it's asking how much work is done. So what is the work done in stretching the spring from its natural length? So this is the natural length, and we're stretching it 6 inches beyond its natural length. So we're stretching it 6 inches. Now that we have the diagrams, let's move on to the second step. Step number 2 says to convert the units on the x-axis. So we're given the force in pounds, so we want to convert it into this one. And since the distance is in inches, we need to convert the inch into the feet. So let me show you how to do that. Now we know that 1 feet is equal to 12 inches. So 4 inches, we want to convert this into feet, and all we have to do is multiply by inch at the bottom and feet at the top. And what this basically does is it's gonna cancel out the inches. So 1 feet is 12 inches, so we get 1/3 feet. Now, how about 6 inches? It is the same thing. So inch times inch at the bottom, feet at the top, and 1 feet is the same as 12 inches. So 6 times 1/12 is the same as 1/2 feet. We replace the inch with the feet, and let's go ahead and do step number 3, which is to find k. Now, from the formula, the force is the same as k times x, and we're given the force as 10 pounds. So the force is 10 pounds, and that is equal to k times x. Now x is the distance that we pulled on the spring, and that distance is from here to here, which is 1/3. So x is the same as 1/3 feet. To solve for k, all you have to do is divide both sides by 1/3. So k is the same as 10 pounds divided by 1/3 times feet. And this is the same as 30 pounds over feet. The fourth and final step is to find the work. So work, we can use this formula. So the work is equal to the integral from A to B of the force times dx. Now we know that the force is the same as k times x. So k times x. And again, k is 30. We found k. So k will be 30 times x. Now, what is A and what is B? A is the start, and B is the end. So this is the start right here, and we pull it until we reach 1/2 feet. So A will be 0, and B will be 1/2. So we have the integral from 1/2. This is 30x dx. So since 30 is a constant, we can move it outside of the integral. So we get 30 times the integral from 0 to 1/2 times x dx. And this is the same as 30 times the antiderivative of x, which is just 1/2 times x to the power of 2. And the limit goes from 0 to 1/2. So we just have to substitute these numbers into this formula. We get 30 times 1/2 times 1/2 to the power of 2, because that's the top limit, minus the lower limit, which is just 1/2 times 0 to the power of 2. This is equal to 30 times 1/2 to the power of 2 is 1/4. So this is 1/2 times 1/4. And whatever times 0 is just going to be 0. So this is just minus 0. And we get 30 times 1/8. And the answer will be 30 divided by 8. And we can simplify this fraction into 15/4. And finally, the unit will be feet-pound right there. So the unit will be feet-pound. And that is the work that it takes to pull the spring from its natural length to 6 inches beyond the natural length. So this right here is our final answer. Let's try another problem. A force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? So go ahead and pause this video and try if you want to. The first step is to draw the diagram. We have a spring, it is at rest, and the natural length is 10 centimeters. So the natural length is 10 centimeters, and it is at rest, so on the x-axis, this point will be 0. Our second piece of information says that a force of 40 newtons, so a force of 40 newtons is required to hold a spring that has been stretched from the natural length. So the natural length is 10 centimeters, and it has been stretched to 15 centimeters. And so the distance between 10 centimeters and 15 centimeters is 5 centimeters. And the question asks us how much work is done. So how much work is done in stretching the spring from 15 centimeters to 18 centimeters. So this is 15 centimeters. We're stretching it from here to here, which is 18 centimeters. The second step is to convert the units on the x-axis. So according to the table I showed you before, we're given the force in newtons. So the distance has to be in meters instead of in centimeters. So let's convert into meters. Now we know that 1 meter, so 1 meter is the same as 100 centimeters. So what's 5 meters? What's 5 centimeters? Well, to convert it into meters, we put meter on top, centimeter at the bottom, and this will cancel out the centimeters. So 1 meter is the same as 100 centimeters, and this times this and we simplify it, it's going to give us 1 over 20 meters. Now, how about 8 centimeters? So 8 centimeters times meters on top, centimeters at the bottom. So 1 over 100, and this is going to be equal to 8 divided by 100. And if we simplify it, we're going to get 2 over 25 meters. We substitute the centimeters with the meters, and the third step is to find K, since it's not given to us. So we know that the force is the same as K times X. We're given the force of 40 newtons. So the force is 40 newtons, and that is equal to K times X. So X is the distance from the natural length, and this distance is 1 over 20. So X is the same as 1 over 20 meters. This means that K is the same as 40 newtons divided by 1 over 20 meters. And when you solve that, this is equal to 800 newtons per meter. The fourth step is to find the work. So the work is equal to the integral from a to b of force dx. Now, the force is the same as K times X, and we found K to be 800. What is A and B? Well, A, the start is right here, so that's A, and this is B, right there. So since 800 is a constant, we can move it outside of the integral. So we get 800 times the integral from 1 over 20 to 2 over 25 times x dx. Now this is the same as 800 times the antiderivative of x, which is just 1 over 2 x to the power of 2. And the limit goes from 2 over 25, and the bottom will be 1 over 20. Now all we need to do is substitute in our limits, so we get 800. This is 1 over 2 times 2 over 25 to the power of 2 minus 1 over 2 times 1 over 20 to the power of 2, and we close the bracket. So this is the same as 800 times 1 over 2 times 2 over 25 to the power of 2. That's going to be 4 over 625 minus 1 over 2 times 1 over 400. Now, we know that we can cancel out the 1 and the 4 up here. And so we're going to get 800 times 2 over 625 minus 1 over 800. Because that's 1 over 2 times 1 over 400. Now we're gonna do this, so we're gonna take this multiplied by this, then this multiplied by this, and we're gonna get 800 times 2 over 625, and 800 times 1 over 800 is just -1. If you simplify this, you get 32. This is gonna be 25. So we get 32 times 2, that's gonna be 64. And the denominator will simply be 25. Now minus 1. When we minus 1, we can just do it as 25 over 25. 64 minus 25 is 39. So we get 39 over 25. And if you put this into a calculator, you get 1.56. And the work is in joules. So this is the amount of work that it takes to pull the spring from 15 centimeters to 18 centimeters. Suppose that 2 joules of work is needed to stretch a spring from its natural length of 30 centimeters to a length of 42 centimeters. A. How much work is needed to stretch the spring from 30 centimeters to 40 centimeters? And B. How far beyond its natural length will a force of 30 newtons keep the spring stretched? So go ahead and pause this video and try it, and then I'll give you the answer. Step number 1 is to draw the diagrams. So if we have a spring and the natural length is 30 centimeters, then this will be 30, and on the x-axis, this point will be 0. We know that 2 joules of work, so 2 joules of work, is needed to stretch the spring from the natural length of 30 centimeters to the length of 42 centimeters. So if we calculate this on the x-axis, 42 minus 30 will give you 12. So the distance from here to here is 12 centimeters. Part A asks us to find the work to stretch the spring from 35 centimeters, so 35 centimeters right here, to 40 centimeters. And to stretch it from this point to this point. And finally, how far beyond the natural length, so how far beyond the natural length, so we want to find x, will a force of 30 newtons, so we get the force of 30 newtons to keep the spring stretched. And that will be the diagram for B. Step number 2 says to convert the units on the x-axis. So we're given the work in joules, we're given the force in newtons, so the distance has to be in meters. Now, we know that 1 meter is the same as 100 centimeters. So what is 12 centimeters? Well, we're gonna multiply by meters over centimeters, 1 over 100. This will give us 12 over 100, which will be the same as 3 over 25 meters. Now, how about 5 centimeters? Well, 5 centimeters times 1 over 100. This is meters, this is centimeters. This will simply give us 1 over 20 meters. And what's 10 centimeters? Well, 10 times 1 over 100. And this will give us 1 over 10 meters. The third step is to find K. Now, we know that the formula is force is equal to K times X, but in this diagram, they give us the work instead. Now, let me show you a trick. If they give you the work, all you have to do is say work is equal to the integral from A to B. So this is 3 over 25, and the bottom is 0. So that's your integral of K times X dx. Now, the work is 2 joules. So all you have to do is just erase this. This is going to be 2 joules. And this equation will allow you to find K. So let me show you how to do that. This is going to be the same as 2 is equal to, since K isn't constant, we can bring it outside. So first, let's bring out the K. Then we get 3 over 25. The integral, this is 0. This is X dx. So 2 is equal to K times the antiderivative of X, which is just 1 over 2 times X to the power of 2. And the limit goes from 0 to 3 over 25. So we're very close to getting K. This is the same as 2 is equal to K times 1 over 2 times 3 over 25 to the power of 2. Minus, when you substitute in the 0, this whole thing would just be 0 right there. This will be 1 over 2 times 9 over 625. This is equal to 2, 1 over 2 times K times 9 over 625. We're going to multiply both sides by 2, and we get 4 is equal to 9 over 6 to 5 times k. So k is equal to 4 times 625 over 9. You're going to get 2,500 over 9. For part A, they want us to find the work by stretching the spring from here to here. So that's pretty easy. So for A, we just use the work formula, which is the integral from A to B. So we get 1 over 10. The bottom is 1 over 20. K is 2,500, which is found, divided by 9 times x dx. So let's bring this outside of the integral, since that's only a constant. We get 2,500 divided by 9 times 1 over 10, the integral 1 over 20 times x dx. And this will be 2,500 divided by 9 times the antiderivative of x, and that's just going to be 1 over 2 times x to the power of 2. And the limit goes from 1 over 10, the bottom is 1 over 20. And let's substitute these numbers into our formula. We're going to get 2,500 divided by 9 times 1 over 2 times 1 over 10 to the power of 2 minus 1 over 2 times 1 over 20 to the power of 2. And we can just close the bracket right there. So this is equal to 2,500 over 9 times 1 over 2 times 1 over 100 minus 1 over 2 times 1 over 400 equal to 2,500 divided by 9. And I'm just going to bring out the 1 over 2. So this is 1 over 2 times 1 over 100 minus 1 over 400. So we can cancel out these numbers. This is going to be 1. This right here is going to be 1,250. So this is equal to 1,250 divided by 9 times 1 over 100 minus 1 over 400. And 1 over 100 is just really the same as 4 over 400. This is equal to 1,250 divided by 9. We get 3 over 400. This is equal to 1,250. And we can cancel these numbers out. So this is 1. This is going to be 3. So the bottom would just be 3 times 1 over 400. Now, we can cancel out the 0 as well. We can cancel out these zeros. We get 1,000 or 125 divided by 3 times 1 over 40. And if we divide the top and the bottom by 5, this is going to be 25. And 40 divided by 5 will be 8. So this would be 25 over 3 times 1 over 8, which is simply 25 over 24 joules, because we're calculating the work. So this right here, this number right here, is the work and the answer for part A. We are so close to finishing. So part B, it's saying how far beyond its natural length, so how far beyond the natural length will a force of 30 newtons keep the spring stretched. So this time they give us the force. And the force formula is K times X. And we want to know how long beyond the natural length. So we want to find X. We want to know how long can it be stretched. We are given the force, and we also know K already. So the force is 30 newtons. K is 2,500 over 9. We found it, right? Remember, we found K. and this is just x. So x is the same as 30 times 9 over 2,500. We can cancel out the zeros like this. So we get 3 times 9 over 250. This will be 27 divided by 250. And if you want to do it as a decimal, this would be the same as 0.108. Just put it into a calculator. And since this is x, the distance is going to be in meters. So we know that if we exert a force of 30 newtons to keep the spring stretched, then the distance that we are able to stretch is 0.108 meters. So this right here is the answer. And this is the same as 10.8 centimeters. So it's up to you if you want to keep it in meters or if in centimeters. These are the answer.